In this problem, we are going to play the part of a crash site investigator. Our job, based on this information, is to try to figure out what the speeds of cars A and B were at the time of crash. So here we go. Car A has a mass of 1,260 kilograms. Car B has a mass of 1,630 kilograms. Car B is traveling 30 degrees north of east. If north is pointing straight up on this picture, east is to the right, so 30 degrees north of east would be that angle right there. The vehicles collide and couple. We know that because we found them at the end of these skid marks when we arrived on the scene. We measured the skid marks, and they are about 44 meters long, an angle of 18 degrees north of east. So I'm showing that on this diagram. The coefficient of friction is about 0.8, and our job is to find the initial speeds of these two cars. Let's draw a free body diagram of the coupled cars. Now, this is not a bird's eye view, this is a ground level view. So we can imagine here are the two coupled cars, and the roadway pavement is right there. And this is a ground level view, not a bird's eye view. These two cars will have a weight. There will be a normal force from the pavement holding them up, and in this case the normal force will equal the weight because there are no other up and down forces. We can calculate what that is. The combined mass of these cars is 2,890 kilograms multiplied by g of 9.81. That gives us a normal force and a weight of 28,351 newtons. Since these cars are sliding to the right, there must also be friction, kinetic friction. Kinetic friction, as we learned in Newton's laws, is always equal to the coefficient of friction times the normal force. Well, the coefficient of friction is given as 0.8, and we know the normal force, so now we know the value of the friction force. Now remember that this V arrow, this is not a force. We're just showing that this mass is sliding to the right. That's it for the forces on this mass. Because we have friction, we're going to use the work kinetic energy theorem. Hopefully you can see the final velocity will be 0. The net force is the force of friction. The normal force and the weight cancel each other, so the net force is simply the friction force. I've put a negative sign in here because the net force and the displacement are in opposite senses. The car is sliding to the right, as I've shown it in this diagram, and the friction force is acting to the left, so we have to put a negative sign there. The mass is 2,890, and we can find the initial speed of this coupled mass at the instant things start happening, and that speed comes out to be 26.3 meters per second, and it's at an angle of 18 degrees north of east because we measured the angle of the skid marks and they turned out to be 18 degrees. So that's where that 18 degrees came from. It came from the previous slide. Once again, this is the velocity of A and B together immediately after impact. So here's what we have. We found that right there the coupled cars have a combined speed of 26.3 meters per second, and the angle is what we found from the skid marks, 18 degrees north of east. If momentum is conserved, let's tackle the y momentum first. Hopefully you can see that car A has no y momentum. It has no up and down, no north-south momentum. Only car B had north-south momentum. So let's calculate the y momentum at the end. Now at the end, the coupled mass does have some y momentum, equal to its mass times its y velocity. Initially, car B had y momentum. There's car B's mass, and car B's y velocity is VBI times the sine of 30. We can solve that for the initial velocity of car B, 28.8 meters per second. And we know the angle, 30 degrees north of east. Let's tackle the x momentum. The x momentum at the end will be the combined mass of A and B times the x component of velocity, which will be 2890 times 26.3 times the cosine of 18. That's the x component of velocity. Initially, here on the far right, the mass of car A times its velocity, which is entirely in the x direction, but car B also had some x momentum at the beginning, equal to its mass times its x component of velocity. Everything is known in this equation except the velocity of car A, which we find to be that. 2 significant figures is the fewest that we have, so we should probably report B's initial speed to be 29 meters per second and A's to be 25. In case you're wondering how many miles per hour that is, about 64 miles per hour for B and 56 for A. Final thoughts on conservation of 2D momentum 3. Here, we tried our hand at a problem that integrated concepts from several units of study in mechanics. From 2D kinematics, ideas with regard to motion, from Newton's laws, drawing a free body diagram, from work energy studies, the work kinetic energy theorem, and from momentum, the conservation of 2D momentum.